If you recall, yesterday we found critical points of a function. And we also have to classify our critical points as local minimum, a local maximum, or neither a local maximum nor a minimum. We were following the same plan that we used to find the optimum values of a function of one variable. Take the first derivative, set it equal to 0, and solve. Find the zeros and any undefined points in the first derivative. Since we always start off with polynomials, we don't have to worry about the undefined points. We just have to worry about the points where the first derivatives are 0. Since it's a function of two variables, we had two first derivatives. We set both of them equal to 0, ended up with a system of equations that we need to solve. In this case, we ended up with a nonlinear system of equations. Your training at this point in solving systems of equations has only been linear systems. If you've been through linear algebra, it was all linear systems. If you've been through elementary algebra, it was linear systems. You're just trying to find where two lines cross. But those strategies are still in play. Those strategies are still in play. In this case, we solve by graphing. So we have options here. We solve by graphing. But we have other options. So the reason I picked solving by graphing is I looked at the two equations. One of them is y equals x. The other one is x equals y squared. So I've got a line and a parabola. I'm just going to draw a picture because I don't even have anything fancy going on. These are like the most basic line and the most basic parabola that you come up with. These two lines are in line to get a pumpkin spice latte at the Starbucks. It is just super basic. But we have other options that we should be aware of. It's going to be especially important if we have equations with three variables, because then graphing is kind of starting to leave the table, because we'd have to imagine a surface intersecting with another surface, and what the heck is that going to look like? So your other option you can also use substitution. This is where you take one equation and plug it into the other. Not literally, that doesn't make any sense at all. That's the way we think about it. We have two equations with two variables. We want to combine those two equations in some fashion to make one equation with one variable. We want to reduce the number of variables running around. So we can also use a substitution. Solve for one of the variables, plug it into the other equation. Solve one equation for one of the variables. Substitute into the other equation. That's a lot to say, which is why I usually say plug one equation into the other equation. Keep in mind the goal. Reduce the number of variables running around. Combine two equations with two variables into one equation with one variable. If we happen to have a situation where there are three equations with three variables, we combine two of the equations with three variables into one equation with two variables. Then grab two different equations with three variables and combine those into one equation with the same two variables you already got. Just reduce the number of variables running around by combining equations. That's the overall goal of solving a system of equations. Whatever actual method you apply, that's what's supposed to happen. So I'm going to take this first equation, x minus y equals 0, and I'm going to write it as y equals x. My other equation says y squared minus x equals 0. Then I'm going to take my y equals x and I'm going to plug it into my second equation. And I'm either going to have x squared minus x or y squared minus y. Solve one equation for one of the variables, substitute that into the other equation. The goal is to get one equation with one variable. And that's what we have here. One equation with one variable. So if y squared minus y is equal to 0, that means y times y minus 1 equals 0. And so that means y equals 0 or y equals 1. Once we have values for y, we can go back to the first equation. And substitute back in. That equation says y equals x. So if y is 0, x is 0. If y is 1, x is 1. If y is 0, then x is 0 as well. And if y is 1, then x is 1 as well. The reason that I'm pointing this out is that if we look back on our algebraic history, only very rarely have we had any experience in solving nonlinear systems of equations. For the most part, we have experience solving linear systems. We learn a bunch of formalized methods. We learn what it represents, but we don't often take those methods and try to apply them to nonlinear systems. So really, the technique for solving nonlinear systems is do something. That's kind of it. It's like do something, which is, of course, the most important thing to do on any math problem. Do something. Any questions? Incidentally, I plugged the, I replaced the x with a y. It would have come out the same if we had placed the y with an x. It would have just said x squared minus x equals 0. That would have given me the same 0 and 1 for x. X and y are the same from the first equation. How's everybody okay? In this case, notice that the first equation has an x and the second equation has a minus x. So we can actually add the equations together and it might actually be useful. That's only because in this case, I have two terms that'll cancel out. We can also use addition and elimination. This is where we add the equations together to cancel out one of the variables. So I could have taken the x minus y equals 0. I'm going to rearrange this one so it says minus x plus y squared equals 0. And if I add them together, the x's cancel out. And so I get minus y plus y squared equals 0. And we're at the same place we were here. Goal still achieved, one equation with one variable. This one is less useful than a substitution because we need to be able to cancel out a variable. If that first equation was x minus y plus x squared equals 0, now this method is just off the table, because I wouldn't be able to cancel out a variable by adding the equations together. So we were kind of lucky in that regard. Although clearly I didn't plan for this to happen. It just, like halfway through these problems, I go, oh snap, I could have done addition method. And I'm like, oh, but you didn't leave enough space, so maybe you shouldn't bring it up. And I'm like, oh, you know me, I can't not bring it up. Why answer a question in 10 seconds when you can take 10 minutes to answer the same question? And include like 9 minutes and 50 seconds of questionable detail. Any questions? So this still brings up the question of what do we do to classify? How do we use the second derivatives to classify the critical points? Because there are 4 of them. There are 4 second derivatives. So fx fx is 24x minus 24y. And I can take 2 derivatives of this function. I can find fxx. I can take the derivative of this with respect to x. So fxx so the derivative of 24x with respect to x is 24. And 24y with respect to x is constant. So the derivative there is 0. The derivative of this of fx with respect to y. Now y is the variable, so x is constant. In this term, x is this just makes a constant term. So the derivative of 24x with respect to y is 0. The derivative of negative 24y with respect to y is negative 24. But wait, there's more. We have 2 variables, which means we have 2 first partial derivatives. Each first partial derivative has 2 variables. So we have a total of 4 second partial derivatives. So I've got fy at xy is 24y squared minus 24x. I can take the derivative of this fy with respect to x. With respect to x, 24y squared is constant, but negative 24x is variable. The derivative here is negative 24. I also have fyy at xy. Now, y is the variable. The derivative of 24y squared with respect to y is 48y. For second partial derivatives. We may notice here that fxy and fyx ended up being the same. This is not a coincidence for this problem. This is usually going to happen. We don't want to say things like, this will always happen. Because then someone like Weierstrass will come along. What if this is your fun? He was the original actuary guy. He was like, oh yeah, you just draw it. I don't have to lift up my pen. I just draw it. Like, oh, and you can do a derivative anywhere? Well, I'm calling them functions, but yes, I can. It's like, well, what about this function that is continuous everywhere and differentiable nowhere? So he was like the first guy that was like, oh, actually, here's a function that is continuous everywhere and differentiable nowhere. So remember back in Calc 1, it's like epsilon delta definition of a limit. Yeah, that's why. It's a very complicated thing. So it's not like I'm disparaging the fact that we have these things, but we had to have limits because we had to come up with something to make this like rigorous and make everything fit together properly. Otherwise, you end up with weird conclusions. So these are usually the same. The mixed partial derivatives, mixed second partials are usually the same. I should call them what they are, mixed second partials. Any questions? Everybody sees the problem, right? I can't just take the point and plug it into the second derivative and see if it's positive or negative. I've got 4 of them. 2 of them are the same, but I've got 4 of them. One counts twice. It's like the polynomial x minus 2 cubed, or the cube of the difference of x and 2, still has 3 zeros. They just all happen to be 2. So it's not like there's one solution to that equation. There are 3 solutions to that equation. They just all happen to be 2. If you don't like that, it's like, oh, but there's only the 2. So find some friends that are twins and say, your mom has 1 kid. They just happen to be the same. Is that acceptable? No. Number of solutions is the degree of the polynomial. There are 4. So those 2 are the same. But be Picard. There are 4 second partial derivatives. Don't be the Cardassian. I only see 3 second partial derivatives. You know what I mean? Does anybody? That's one episode of Star Trek: The Next Generation. Just one. I don't know if anybody's seen it. Has everybody seen that one? Have you not watched Star Trek: The Next Generation in its entirety? I thought you guys were like engineers and stuff. That's on the test, by the way. When you want to graduate, get your bachelor's degree, there's like a whole section of the test on Star Trek. And you have to know all of it, every single series. I'm just kidding. But it is a test to get into graduate school. You're going to go sit down in the graduate record exam and like, well, what are all these Star Trek questions? And if you even ask that question, they just throw you out. I'm just kidding. You need to know all that stuff for your master's degree. I'm just kidding. You can substitute knowledge of Star Trek with 3 other less common sci-fi series. So you say, well, I'm not going to take the Star Trek exam. I'm going to take the Dune. I gotta think about Stargate and Farscape exams. I was like, okay, if you do all 3 of those, that'll get you the sci-fi equivalent of the Star Trek. Okay. Star Wars is generally not acceptable. I mean, you should just perform, but it's not like required. And if a school does require Star Wars, that school is just not taking itself seriously. You know what I mean? I'm just kidding. I love Star Wars, even though there's only like 2 movies that I actually like out of the whole series. 2 movies that actually don't pass that pass the refrigerator. Most of the movies pass the refrigerator test. But there's movies that I like that I just can't think about very much. So if someone's like, well, you know, when you think about Star Wars, I'm like, oh, no, come on. I actually like that movie. I had fun during the movie. So just stop right there. Because I don't want to think about it, because I know if I start thinking about it, I'm going to be annoyed. Stop. You know what I'm talking about? Does everybody know what the refrigerator test is? Do people watch movies? My God. What are they teaching kids in high school these days? The refrigerator test was invented by Alfred Hitchcock. If you go to a movie and you enjoy the movie, you walk out of the movie and everything was awesome, and someone says, hey, how was that movie? And you're like, oh, it was great. I loved it. All you have to do to be classified as a good movie is it makes it to the refrigerator for your midnight snack. If you get all the way to your refrigerator, midnight snack, that movie was so cool. Grab out the sandwich, start piling stuff up, you sit down, it's past the refrigerator test. Now, if you're sitting down having that midnight snack, you're like, oh, you know what? That was kind of stupid, that one part. Doesn't matter. You enjoyed the movie. You said it. You don't get to make a video on YouTube about it now and start crying that it wasn't very good. It was good enough to get that far. Movie wins. You know what I mean? Everything else is just YouTube crying about it. You know what I'm talking about? Don't think about your favorite movie very much. It's gonna fall over. You know what movies will not do that to you? The greatest movie franchise of all time, The Fast and the Furious. Because you're watching The Fast and the Furious and you're like, oh, this is patently stupid. This is objectively stupid. And you don't care. So it doesn't matter if you think about it later on and think that part was stupid. It doesn't occur to you later that that part was stupid because the whole thing was stupid right from the jump. You know, they go, oh man, why is the force working that way? What the F, midichlorians? Now, to be fair, that pissed me off in the theater. I was like in my theater seat at the most anticipated film of all time. And I was like, oh, the F is this? In the seat, watching Darth Vader go, yippee! Very angry. To be fair, I had a lot of baggage. Like I said, that was, I think objectively, the most anticipated film of all time. Prove me wrong. Prove me wrong. I know you weren't alive when it happened, so I shouldn't be all blaming you, but it's all your fault. I'm just kidding. I don't blame young people for things. I'm not a boomer, for Christ's sake. Incidentally, if you're a boomer and you're listening to me, cry more, boomers. You ruined the world. What are we talking about? Oh, yeah. Mixed second partial derivatives. How did this happen? There are 4 mixed second partial derivatives that cause Star Trek, that cause. Okay, I see where it came from. I don't know if this is a more coffee problem or a less coffee problem, but I know what solution I'm going to apply. Mixed second partials are usually the same, but you still have 4 of them, which is that 2 of them are twins. Here's the problem. We can't just plug in, because if I plug into this one, it's positive, right? And so, positive, concave up, minimum. Oh, hang on. There's 2 that are negative. Concave down, maximum. Wait a second. 48y. It's positive at this one, so concave up, minimum, but negative in the. There's 4 of them. We have to combine them in some fashion. So here's how we're going to combine them. I didn't have enough space to write the of xy's, but at each point, you make this calculation. fxx times fxy minus fxy squared. We can get away with that because, like we mentioned previously, the mixed second partial derivatives are usually the same. So fxy times fyx will be the same as fxy squared. Oh my gosh, I spelled xy and I'm supposed to say fyy. This is why I shouldn't do this on a Friday. Well, I brought up the whole card thing in the first place. fxx times fyy minus fxy times fyy. If you're thinking that has a very determinant-like structure, you are correct. It has a very determinant-like structure. It's a determinant that was built with fxx, fxy, fyy, fyx. Or maybe we switch these. It doesn't matter. For our purposes, we just need to know how to combine these 4 second partial derivatives to classify our critical points. I suppose I need to tell you how this works. You may be like, well, that's not enough to know how this works. So if this value D is positive and fxx is positive, that's when we get to say the same thing as before. Concave up, local minimum. that fits with what we talked about before. This is where if D is positive and fxx is positive, then we get to say local minimum, because we're thinking it's like concave up. A second derivative is positive, that's concave up, that's local minimum. Oh, wait, blue were those conclusions. If D is positive and fxx is negative, then local maximum. So if D is positive, we look at the second derivative, xx, and we make a conclusion similar to our concavity conclusion from before. This fxx, this is similar to when we said the second derivative is negative, which means our function is concave down, which means we have a local maximum. That ties it to the same conclusion structure that we had before. Second derivative positive, concave up, local minimum. Second derivative negative, concave down, local maximum. For critical points, critical points. Pause for copy. Oh, wait, don't do that. Notice that I'm only doing this second derivative, making this second derivative observation based on one of my second derivatives, the fxx. But that's not the only thing that we're looking at. We're also noticing that the D part is positive. That determinant is positive, and fxx is positive, or fxx is negative. So we only get to do this one if this one is also the case. So we also have to consider what happens if that D calculation is negative. If this determinant D is negative, then we have what's called a saddle point. Remember, we have two directions. What's going on at a saddle point is that in one direction we'll have a local maximum, in the other direction we'll have a local minimum. And so it makes this saddle shape. There's like the local maximum, that's the direction that you put your legs over the horse. And then there's the local minimum, that's the saddle going behind you and up in front of you a little bit that you sit in, that keeps you from falling over forward, even though it's really easy to fall over forward on a horse, because the saddles don't go up that high. You know what I'm talking about? Anybody ridden a horse? It's an expensive hobby. It's an expensive activity. I shouldn't call it a hobby. It's too expensive to be a hobby. It's an activity. It's a lifestyle. So here's how we make our conclusions. What's one of the things I left out? I have not covered everything yet. D is positive and negative. That covers everything, right? If D is equal to 0, then we have. Here's what you need to do. It's Friday. And I delayed the perfect amount of time to run out of time for when D is equal to 0. Here's a question that you have that you need in your mind. Why is D positive negative? Why does that allow me to just look at fxx? How can I get away with that? What if D is positive? What does that mean? If D is negative, why does that automatically indicate saddle point? I've already told you what the answer is, but you need to put the answer together in your mind. Why is this? If D is negative, then we have a saddle point. How can I be so bold and not look at anything else and just say D is negative, saddle point? How can I make that conclusion? All right, that's it for today. I will see you all on, that's it for this week. I will see y'all on Monday. Everybody have a good weekend, and thanks for playing.